Dear students, welcome to my YouTube channel Hardik Joshi. Today we will discuss 12th Physics, chapter number 4, Moving Charges and Magnetism, exercise example. In last video, we explained exercise example number 4.1 to 4.8. Now here we will start from example number 4.9. Okay. So question of example number 4.9 is a square coil of side 10 cm consists of 20 turns and carries a current of 12 ampere. So here we have different value. The first value is given, okay, that is length of side of square 10 cm. Therefore L is equals to 10 cm. Convert this value into meter. So it is 0.10 meter. It consists of 20 turns. So number of turns capital N are 20, okay, and carries a current of 12 ampere. So current I is equals to 12 ampere. Remember one more point, this is a square coil, okay. So for square coil, area A is equals to L square. L square means 0.1 whole square. So area of coil is 0.01 meter square. Okay, length is given. From the value of length we can find area of square. It is A is equals to L square. So here we have value of area 0.01 meter square. Number of turns are 20. Current passing from coil is 12 ampere. Okay. Now here we consider the coil is suspended vertically and normal to plane of coil. Okay. So here we have normal arrangement of coil. Okay, normal to plane of coil, and makes an angle of 30 degree. So the value of theta is given, theta is equals to 30 degree, okay, with the direction of uniform horizontal magnetic field of magnitude 0.80 Tesla. So here magnitude of magnetic field is given, B is equals to 0.80 Tesla. What is the magnitude of torque experienced by coil? So here we want value of torque, okay, the torque experienced by coil. This is most important equation, okay. The torque acting on current carrying coil is given by vector tau is equals to vector M cross vector B. M means magnetic moment, okay, and B means magnetic field. Consider only magnitude and remove the cross product. So equation of tau is equals to MB sin theta. Now M means magnetic moment, but equation of magnetic moment M is NIA, number of turns into current passing from coil into area, okay. So use equation of small m, M is equals to NIA. Therefore tau is equals to NIA into B sin theta, okay. Instead of small m, here we use equation NIA. So NIA into B into sin theta. Substitute all value. Number of turns are 20. Current passing from coil 12 ampere. Area of coil 0.01 meter square. Applied magnetic field 0.80 Tesla, and here we have sin theta, sin 30 degree. The value of sin 30 degree is 1/2. Okay, so substitute all value and find your final answer. So torque acting on a coil tau is equals to 0.96 Newton into meter. Okay, so this is the value of torque, deflecting torque acting on a coil 0.96 Newton into meter. Another example, example number 4.10. This is most important example of this chapter. We have two moving coil galvanometer. So two moving coil galvanometer M1 and M2. First moving coil galvanometer is denoted by M1. Another moving coil galvanometer is denoted by M2. They have following particulars, following quantity. So for first galvanometer, resistance R1 is equals to 100 ohm. Sorry, resistance R1 is equals to 10 ohm. Number of turns are N1 is equals to 30. Area of first galvanometer, coil of first galvanometer 3.6 into 10 raised to minus 3 meter square, and applied magnetic field is 0.25 Tesla. So these are your quantities for first galvanometer, okay. For first galvanometer means for M1. Similarly for M2, second galvanometer, resistance R2 is equals to 14 ohm. Number of turns N2 is equals to 42. Area A2 is equals to 1.8 into 10 raised to minus 3 meter square, and applied magnetic field is 0.50 Tesla. Okay, the spring constant are identical. Spring constant are identical means spring constant for first galvanometer is equals to spring constant of second galvanometer. K2 and K1 both are equal, is equals to, we use common symbol K. Okay, determine the ratio of current sensitivity. Okay, first point, find the ratio of current sensitivity and voltage sensitivity of M2 and M1. M2 means second moving coil galvanometer with respect to M1. Okay, first moving coil galvanometer. So here we have 4 value for first galvanometer, R1, N1, A1, B1, and 4 value R2, N2, A2 and B2 for second galvanometer. So first of all we find the value of ratio of current sensitivity. Now for a galvanometer we have this equation of torque. This is the equation of torque. Deflecting torque NIAB is equals to restoring torque K5. So NIAB is equals to, we can write K5, N number of turns, I current, A area, B magnetic field, K is known as torsional constant and value of K remains same for both coil. Okay, K1 is equals to K2 is equals to, here we use K symbol. Effective torsional constant or torsional constant are equal for both coils. And phi is deflection. Okay, the phi is known as deflection of coil. Now first of all we find ratio of current sensitivity. So remember equation of current sensitivity. Current sensitivity is equals to phi upon I. So if we make equation of phi upon I, so we can write phi upon I is equals to NAB upon K. Now this is our equation of current sensitivity. Now we want ratio of current sensitivity. Current sensitivity of M2 upon current sensitivity of M1 is equals to, for second galvanometer. Okay, here we have current sensitivity for second galvanometer. So we use this equation. For second galvanometer we use N2, A2, B2 upon K remains constant, so as it is. Okay, so for second galvanometer here we will use N2, A2, B2 upon K divided by current sensitivity of first galvanometer means N1, A1, B1 upon K. Okay, here K get cancel out, so our final equation is N2, A2, B2 upon N1, A1, B1. This is the ratio of current sensitivity of M2 to current sensitivity of M1. Okay, so substitute all value. N2 42 number of turns in a second galvanometer, A2 1.8 into 10 raised to minus 3, B2 0.50 Tesla divided by N1 30, A1 3.6 into 10 raised to minus 3 meter square, and magnetic field B1 0.25 Tesla. Okay, using calculator find your final answer. So your final answer is 7.5. Okay, so current sensitivity of M2 to current sensitivity of M1. Okay, current sensitivity of M2 divided by current sensitivity of M1 is equals to 1.4. So the ratio of current sensitivity for both galvanometer is equals to 1.4. Now second point, here we want ratio of voltage sensitivity also. So voltage sensitivity is equals to phi upon V. Deflection per unit voltage is known as voltage sensitivity. Deflection phi as it is, but V according to Ohm's law, V is equals to, we can write IR. So instead of V here we use equation IR. Now phi upon I, this is nothing but this is deflection per current, and deflection per electric current means current sensitivity, and we already discussed its equation. So phi upon I is equals to, we have equation NAB upon K, and here we have capital R. Capital R means resistance as it is. Okay, so this is your equation of phi upon V means phi upon IR. Therefore we have phi means phi upon I is equals to NAB upon K and R as it is. So voltage sensitivity phi upon V is equals to NAB upon KR. We want ratio of voltage sensitivity. So voltage sensitivity of M2 divided by voltage sensitivity of M1 is equals to, this is our equation of voltage sensitivity. Use this equation for second galvanometer. Okay, so here we can write N2, A2, B2 divided by KR, K as it is, but resistance of second galvanometer is different, so we use symbol R2, divided by voltage sensitivity of M1. Use same equation for M1 galvanometer. So we have N1, A1, B1 upon divided by KR, so K as it is into R1. Okay, see the equation very carefully. Here K get cancel out. Redistribution, rearrangement of this equation. So here we have N2, A2, B2 upon N1 A1 B1. Here we have R2. R2 is in a denominator and R1 is in a numerator. So we can write N2 A2 B2 upon N1 A1 B1 bracket over. Here we use R1 into R2. Now substitute all value, but see the term in a bracket very carefully here. N2 A2 B2 upon N1 A1 B1. This is nothing but this is current sensitivity of M2 to current sensitivity of M1. So here we use, instead of this bracket, we use current sensitivity, the value of current sensitivity of M2 to current sensitivity of M1 into R1 upon R2 as it is. Already we found the value of current sensitivity of M2 with respect to current sensitivity of M1, and it is 1.4, okay, or 7 upon 5. So we use this value here, 1.4 into R1, resistance of first coil of galvanometer is 10 divided by resistance of second coil of galvanometer is 14. So find your answer. So voltage sensitivity of M2 divided by voltage sensitivity of M1 is equals to 1. So this is the ratio of voltage sensitivity of galvanometer 2 with respect to galvanometer 1. Next example. Example number 4.11. In a chamber, a uniform magnetic field of 6.5 Gauss. See the unit of magnetic field. Here we use capital G symbol. Capital G is used for Gauss. And remember its conversion in Tesla. 1 Gauss is equals to 10 raised to minus 4 Tesla is maintained. Okay. So in a chamber we have this amount of magnetic field 6.5 Gauss. 6.5 Gauss means 6.5 into 10 raised to minus 4 Tesla. An electron is shot into the field with a speed of 4.8 into 10 raised to 6 meter per second. So the speed of electron is given. Normal to field. Normal to field means here we consider theta is equals to 90 degree. This is normal motion of electron. Explain why the path of electron is circle. Okay, here electron moves on circular path. So you have to give your answer why path of electron is circle and determine the radius of circular orbit. Okay, so here we found the value of radius of circular orbit. Magnetic field is given, okay, and speed of electron is given and angle theta is also given. So here we consider perpendicular motion of electron in the magnetic field. So the perpendicular magnetic field exerts exert a force on the electron normal to path, okay, and this force continuously deflects the electron from its path and makes it move along a circular path. So remember this point here, motion of electron is normal to magnetic field. So magnetic force continuously deflect electron from its path and finally electron moves on a circular path. So this is the reason, okay, for circular motion of or circular path of electron. This is possible if theta is equals to 90 degree. Okay, if magnetic field is normal to velocity of charged particle, we always consider circular motion of electric charge, okay, or electric charge moves on a circular path. Now here values are given. Magnetic field B is equals to 6.5 Gauss means 6.5 into 10 raised to minus 4 Tesla. Clear? Convert the value of Gauss into Tesla by multiplying number 10 raised to minus 4. Velocity of electron is given 4.8 into 10 raised to 6 meter per second. Find the radius of circular path. So we have standard equation of radius. Radius r is equals to mv upon qb. M is mass of electron. It is 9.1 into 10 raised to minus 31 kilogram. These are standard constant. Velocity of electron 4.8 into 10 raised to 6 meter per second. Charge of electron, this is also standard value, 1.6 into 10 raised to minus 19 coulomb. And applied magnetic field 6.5 into 10 raised to minus 4. Be careful about this unit. Gauss is not a SI unit of magnetic field. You have to convert your value into Tesla. Okay, so here we multiply this number by 10 raised to minus 4. So your answer is in a Tesla. Try to solve this mathematical step using calculator. So radius of circular path r is equals to, here we have value 4.2 into 10 raised to minus 2 meter. Okay, 4.2 into 10 raised to minus 2 meter. This is the radius of circular path. Next example, example number 4.12. okay, in exercise example 4.11, so here we will use quantities of our example 4.11. obtain the frequency of revolution of electron in its circuit, okay, in its circular orbit, in its circular orbit, in its circular orbit. Does the answer depends on speed of electron? Explain. So here we want frequency of revolution, nu. So the frequency of revolution of electron in orbit is given by, this is our standard equation, nu is equals to qb upon 2 pi m. This is the equation of frequency of revolution. Okay, you have to remember this equation, nu is equals to qb upon 2 pi m. Q means charge of electron 1.6 into 10 raised to minus 19 coulomb. Magnetic field 6.5 into 10 raised to minus 4 Tesla. In this example, we will use quantity of exercise example number 4.11. Okay, and in 4.11 example, this value is given, divided by 2 as it is, pi means 3.14, and mass of electron is 9.1 into 10 raised to minus 31 kilogram. Okay, so this is your mathematical step. Find your final answer. So nu, frequency of revolution, nu is equals to 18.18 into 10 raised to 6 hertz. Be careful about this value. 10 raised to 6 is equals to, we can write mega symbol, capital M. So frequency nu is equals to 18.18. 18.18 is equals to, here we will use only value 18, and 10 to the power 6 is equals to, we use our special symbol capital M. Okay, multiple mega. So nu, frequency of revolution, nu is equals to, we have value 18 megahertz. And see the equation of frequency. The frequency of revolution does not depends on velocity. Okay, so the frequency does not depends on speed or electron. So frequency nu always remains constant. The value of frequency in this example remains constant. Okay, because frequency does not depends on velocity. And the last example, example number 4.30. A point, a circular coil of 30 turns and radius 8 centimeter carrying a current of 6 ampere. So we have first value, we have circular coil, number of turns in a circular coil are 30, radius of circular coil is given 8 centimeter, current passing from circular coil is given 6 ampere, suspended vertically in uniform horizontal magnetic field of magnitude 1 Tesla. So magnetic field, these 4 quantity are given. Okay, number of turns, radius, current, and magnitude of magnetic field. So these 4 quantity are given. The field lines make an angle 60 degree. Fifth quantity is given, theta is equals to 60 degree with the normal to coil. Calculate the magnitude of counter torque that must be applied to prevent the coil from turning. So here we want magnitude of counter torque. Counter torque means restoring torque. Okay, so first of all we separate given value from this example. Number of turns are given 30, radius of coil is given 8 centimeter. 8 centimeter means 0.08 meter. Current passing from coil 6 ampere. Applied magnetic field is 1 Tesla. Angle is given. Okay, field lines makes an angle 60 degree with the normal to the coil. Okay, theta is equals to 60 degree. Find counter torque, tau. Okay, so here the magnitude of counter torque is equals to magnitude of deflecting torque. So in equilibrium condition, the value of counter torque means restoring torque, is equals to magnitude of value of deflecting torque. And we have equation of deflecting torque. Deflecting torque is given by NIAB sin theta. This is the equation of deflecting torque, NIAB sin theta. Therefore magnitude of counter torque, okay, counter torque means restoring torque, tau is equals to NIAB sin theta. Okay, so here tau is equals to number of turns as it is, current as it is. Here we have area of coil, the value of radius is given. Okay, so here we use area, A is equals to equation pi r square to find area of coil. This is the equation of area of coil. So area A is equals to pi r square, means area of coil. So equation of torque is tau is equals to Ni into pi r square into B sin theta. Substitute all value. Number of turns 30, current 6 ampere. Okay, it is given in our question. Pi as it is 3.14, r square, square of radius 0.08 whole square. Be careful about this CGS unit. Radius is given, okay, it is 8 centimeter, and here we have CGS unit of distance 8 centimeter. So convert this value into meter. Okay, divide this value by 100 or multiply this value by 10 raised to minus 2. So it is 0.08 meter. Magnetic field, applied magnetic field is given. B is equals to 1 Tesla, and sin theta means sin 60 degree. The value of sin 60 degree is √3/2. Okay, and find your final answer. So the magnitude of counter torque means magnitude of restoring torque is 3.13 Newton. Okay, so this is our A question. And B point, this is our answer of A point. B point, would your answer change if the circular coil in A point were replaced by planar coil? In A point we use circular coil, but if we replace circular coil with planar coil, would your answer changes? Okay, for some irregular shape that encloses the same area. So here we have a planar coil having same area as circular coil. So your answer is no. The answer would not change because the formula of torque is true for planar loop of any shape, because the formula of torque tau remains same for both type of loop. We will use this equation for planar loop, okay, as well as we will use this equation for circular loop. So this equation is valid for both loop, remains same for planar loop and circular loop. So the value of torque does not change, it remains as it is. Okay, so your answer is in B point, it is also 3.13 Newton into meter.